So now in lecture 5, electric fields in matter. So in this chapter, in this lecture, what we are going to learn is we are going to deal with the situation where you have materials, and the material, of course, respond to the electric field. So the situation is very different from the free space. So through this lecture, what I want you to understand is the reason why we have both D and E field. So let's recall what we learned in the previous lecture. We in like free space electrostatics. Electric field E was enough, right? There was no need to introduce any further quantity, right? But if you recall the Maxwell's equations, people always write E and D for electric field. These two are different things, right? And then what I want to answer through this lecture is why we need two different things. Like in which case we need to distinguish E and D field. So that's the question that I want to answer through this lecture. And just to tell you the short answer, D is required or makes your life more convenient when there is a material. So D field is developed in order to describe the situation where materials exist. Okay, so let me begin with this. So materials can be classified into many different ways, but one interesting way to classify the material is the material depending on their conductivity. So if you can classify a material as conductor, semiconductor, and insulator. Insulator, even though you apply the voltage, there's no current. Conductor, if you apply the voltage, there's a flow of electric current. Semiconductor, it's in between. It's not like absolutely zero current, but it's very small amount of current. Okay, and then that value, the amount of current, changes as a function of temperature or other external stimulation. So in this lecture, we're gonna first deal with insulator, and then conductor. And semiconductor is in between. So if you know about insulator and conductor, and you also can deal with semiconductors. So let's think about how material respond to a applied electric field. So to do that, we want to first define polarizability. Polarizability is alpha, okay? And then E is electric field at the position of atomic site. And then P is induced dipole moment. You remember that we learned dipole. What was dipole? Dipole is like plus and minus charges separated by distance d. And then dipole moment was qd, right? You remember. And then this, the direction was like this. And then what this tells you is this situation. So imagine you have a atom. Atom has a nucleus and then electron cloud. When there's no electric field, the center of the nucleus and the center of the electron clouds are kind of coincide. So there's no dipole moment at all, okay? But if you apply the electric field, say like this, then what happens is that nucleus wants to go this way because it's plus charge, and then electrons wants to go that way because it's negative charge. So for the same electric field, electrons and nucleus feels the force in opposite direction. And due to that force, when there is an electric field, there is a small dipole moment created, right? Because the center of the electron cloud is now not exactly matches to the position of the nucleus. So you have non-zero dipole moment, right? P. And then that dipole moment is induced by electric field E. And alpha connects these two. When electric field is applied, you have your atom becomes a dipole, and then that dipole moment and the electric field is connected by polarizability. Okay, and then we say that your atom becomes polarized, right? Polarized means it's like separate. The two charges are separated. And then same thing applied to the molecules. Like if you remember how your water molecule looks like, it's H2O, and then H tends to be positively charged, so tends to lose its electrons, and then oxygen tends to gain electrons. So when they form a molecule, oxygen is negatively charged, and then hydrogen becomes positively charged, right? Now, if you apply an electric field, so this one, by the way, so the water molecules are naturally polarized. It has dipole moment from here to here. This is the dipole moment of water molecule. And then when there's no electric field, these water molecules are randomly oriented, right? Like this, randomly oriented. So if you calculate the net dipole moment, it's 0 because it's randomly oriented. But when the electric field is applied, then these dipoles tend to align to the applied electric field, right? And this is natural thing because when electric field is applied, positive charge wants to go this way, negative charge wants to go that way. So it's naturally aligned like this along the electric field, right? So the electric field outside and electric field inside are very different, because electric field outside and electric field inside, you should take into account the contribution from the dipole electric field too, right? So this is what's happening inside the material when there's an applied electric field. Okay, very complicated, right? If you want to take into account the response of every atom, it will be a disaster. It will be really difficult to deal with. So instead of doing that, we want to make okay, so there's one question I would like to answer. So Kim Junmo asks, in H2O example, if H is plus Q and then O becomes minus 2Q, then how we can define a dipole moment? Well, we can do it this way. We can divide the system like this: Q and minus Q, and then minus Q and plus Q. So this is a summation of two dipoles. So this dipole and that dipole, right? And then in each dipole, there's no ambiguation. And then once you evaluate the vector dipole moments, we can just add them up to get the total dipole moment. That's how we define P, total dipole moment. The vector summation of two. So how to deal with it? How to deal with every atom in the material? It's something we cannot do. So instead of doing so, we introduce average concept. So we introduce large P, capital P field, which is called polarization field. This is nothing but a dipole moment per unit volume. So you can add all the dipoles in the dipole moments in a given volume, and then divide it into delta B. So it's like take the volume average, and then making the volume to infinitely small, and then you can define your dipole moment. Now your system becomes continuous, right? If you imagine like atomic system or molecular system, your dipole moments are located at the position of atom or position of a molecule, which is discrete. And then instead of doing so, we can define a polarization field, which is a volume average of it. It becomes a continuous field, right? And then electric potential due to induced dipole. If you want to calculate the electric potential due to induced dipole, you can do this. Okay, you can just do P dot AR dV 4 pi epsilon naught R squared. Okay, so volume, the potential of an induced dipole is this. And then we learned this in the previous lecture. You probably remember when we have a dipole, the electric potential due to a dipole have this form, right? We took it from that page. And now this part, the AR direction divided by R squared can be written as this. This is just a vector relation. So you can just take it. You can just take it as true. Okay, so you can do that. And then from here, you apply a vector relation like P dot gradient of 1 over R is equal to this. Gradient of P over R minus 1 over R divergence of, I'm sorry, this is also divergence of P. So that this is another vector relation that you can just take it. And now if you do this mathematical manipulation, then you now see this relation is familiar to you. So if you do, so this part you apply the divergence theorem, okay? Then your volume integral becomes surface integral. And then this part, you can just leave it as a volume integration. Interesting part is that if you look at the dependence, it's 4 pi epsilon naught R. And this one is also 4 pi epsilon naught R, which is a dependence of, this is how surface charge and volume charge depends on, so this is how like electric potential looks like for a surface charge and volume charge, right? You probably remember this. V is equal to rho S 4 pi epsilon naught R ds, and then also rho V 4 pi epsilon naught R dV, volume integration, surface integration. So this is how you evaluate your potential from surface charge distribution and volume charge distribution. So you can interpret this term as your surface charge. And then you can interpret this term as your volume charge, right? So P dot AN gives you surface charge, and then negative divergence of P gives you volume charge distribution due to the polarization, right? So we can call this as a bound charge density. Okay, the reason why it's called bound is because it's not a free charge, it's a bound charge. So if you apply the electric field, this material doesn't allow you to have a current, right? There's no current flow. Instead, your materials becomes polarized, right? And then act as if you have a surface charge and volume charge. And this is called a bound charge densities. So by the way, Kang Yung asks why we have prime here. Oh, yes. Prime is the gradient only applies to the primed coordinate variables. And also dV has prime because we are talking about the source positions in this case. Okay, An Donghyun asks, yeah, so right. So AN is like the direction normal to the surface. Yes. Unit vector normal to the surface. Okay. So long story short, I don't want you to kind of memorize everything here, and it's not actually too important to understand like all the steps here. But what I want to convey here is that if you apply the electric field, materials inside becomes polarized, right? The molecules and atoms inside that dielectric becomes polarized, right? And because of this polarization, you have a different electric field inside the material. And in order to describe that effect, we introduce the concept of bound charge density. Instead of dealing with every dipole moment, we just make it into a bound charge density. And then bound charge density can be easily calculated from the P field. And P field is the volume average of the dipole moment. So P dot AN gives you surface bound charge. And then gradient of P, divergence of P gives you volume bound charge. And then I'll keep remind you about this concept throughout the lecture. So if you don't understand it now, it's not a big problem. Okay, so now in a dielectric material, in an insulating material, you now understand that the charge can be divided into two parts. One is the free charge, and the other is the bound charge. Bound charge is created as a response of a material. So that's kind of different thing. Free charge is something you can just freely move around. Okay. And now, free charge, if you rewrite this equation, free charge is the total charge minus bound charge. And then we define, so the total charge by Gauss law, it looks like this, right? Epsilon 0, divergence of E. Because Gauss law holds anyway, but you have to take into account all the charges. So that's the total charge. And then we previously defined that the bound charge density is minus divergence of P, the polarization field, right? So if you add them up, you have a divergence of epsilon E plus P, right? And then we call this as a D field. Okay. We call this as a D field. So from this, it's obvious, like we have rho FV, which is equal to divergence of D. So D field is introduced in order to describe the free charge contribution of the electric field. Okay. whereas E field is about the everything. Okay, so here's the important distinction is that the charge that we can freely control is the free charge. So it's good to know how, good to define the field component that is associated with only the free charge. So that's the reason why we have D field. And then you will see why this is useful as we continue the lecture. And here again, we define the relation between E field and P field. E, again, is about the total electric field. P is the polarization field. And these two fields connected by chi E epsilon naught. Epsilon naught is a constant, right? It's just a 8.85 something times 10 to the minus, I forgot, 9. Anyway, epsilon naught is just this is just a constant, and chi E depends on material, and we call this as electric susceptibility. Okay, so when electric susceptibility chi E is high, that means this material is very easily polarized, right? So if you apply the electric field, it becomes easily polarized, so you have a large P field. And then when chi E is small, that means that material is hardly polarized. So in the extreme case, if chi E is 0, then no matter how large the electric field is, you get 0 polarization, which is like in vacuum, right? In a free space, there's nothing to get polarized. In that case, chi E is 0. And then we can also define a relative permittivity, which is 1 plus chi E. So if you define, which is called epsilon R, or dielectric constant. And if you define it this way, D is epsilon E plus P, and epsilon 1 plus chi E plus times E. And then this thing is epsilon R. So, and then if you add, multiply these two, we call it as just epsilon without 0. Okay, so 0 represents, in most of our lecture, 0 represent vacuum or free space. And then if you write something without 0, that means it's about some material. It depends on material. Okay, so these are just the definition. What I want you to keep in mind is just the flow. If you have a material, your material becomes polarized due to the applied electric field. And in order to describe that polarization, you need P field. And the P field is associated with bound charge density. And then in order to describe the free charge contribution, you introduce D field. And then total charge is connected with E field. Okay, so I guess now it's clear. And here's some more about the susceptibility and permittivity. Well, in actual material, epsilon is not a constant number. Epsilon itself depends on the applied electric field intensity. Okay, and then epsilon actually is not even a scalar function. It's actually a rank 2 tensor, like 3 by 3 matrix. Okay, and then like something like this is possible. Like if you apply the electric field in X direction, polarization can happen in Y direction, right? Then that's associated with what's that? The X to Y component. Like this term is non-zero in this case. So in general, to deal with dielectrics permittivity in a proper manner, you need to consider epsilon as a matrix, and each component of the matrix should depend on the electric field intensity. But that's kind of too much, right? That's kind of too much for this course. So we assume a linear and isotropic case. So in our lecture, we just assume that E is not dependent on electric field. Epsilon is not dependent on electric field, and epsilon is not a matrix. It's just a scalar. Okay, just a number. And here's the dielectric constant of real materials. There's a vacuum, of course, it's 0. I'm sorry, 1. Susceptibility is 0, and the permittivity is 1. And then air is almost like a vacuum. Of course, in the air, there's an oxygen, nitrogen, or many other stuffs. But if you think about it, oxygen doesn't have polarity, right? And then molecule. And then nitrogen molecule also doesn't have polarity. So, and water molecule has polarity, but it contains very little water molecules in the air. So air is also very, very, epsilon is very close to 1. And then benzene, diamond, and salt. These are famous dielectric materials. And then you can see the epsilon is now largely deviate from 1. And then silicon, methanol, water, these things are has even higher dielectric constant. And then extreme case, KTANNBO3, like I don't know how to even call this, but this material has a dielectric constant of a few tens of thousands, which means this material is extremely easily polarized. With a very small amount of electric field, this material is polarized, strongly polarized to produce the polarization field. Okay, so here's another another interesting concept about the dielectrics. So now you assume that you have a dielectric material. Okay, and then this dielectric material, and then you apply the electric field. And then, as I said, this dielectric material is insulating, so there's no current flowing. And instead, you have a bound charge formation, and then this dielectric becomes polarized. That's what we learned. But this is not the end of story. If you increase the electric field intensity higher and higher, then what happens is that in the end, this dielectric undergoes a phenomena called breakdown, and then current flows instantly, and then this is called dielectric breakdown. And then everyday life, we experience this like in this in winter, when we try to touch a metal doorknob, we feel this zap between your hand, your finger, and the metal doorknob, and there's a current flow. Okay, and this is a kind of a microscopic incarnation of lightning. So lightning is the dielectric breakdown of the air. So what happens is that as the water molecule or ice particles moving around, they become charged, and then the charge accumulation between the end of the bottom of the cloud and the top of the Earth's surface becomes higher and higher, and there's more electric field accumulated, like higher electric field accumulated, right? And this electric field becomes higher than certain value, then all of a sudden current flows, and that's lightning. And that's the famous example of a dielectric breakdown. So dielectric breakdown of the air is 3.0 megavolt per meter. Megavolt per meter, volt per meter is the electric field intensity. Benzene, it's higher, diamond even higher. Glass, it's like this, water, alumina, fused silica. And you can see if you apply extremely large amount electric field to the dielectric, it becomes conducting, like through dielectric breakdown. And that's how much it can resist. Okay. And in terms of vacuum, you probably feel this is very strange because vacuum means there's nothing, right? So there's nothing, but somehow if you apply extremely large dielectric strength, extremely large electric field, current flows. How come this is possible? Because there's nothing, right? So nothing to break down. The thing is, you probably heard about this quantum fluctuation. Like vacuum is actually not a vacuum. The vacuum is sort of the state where you have like antiparticle filled up, and then there's no particle above certain energy level. So like even in a vacuum, if the applied electric field is high enough, this particle antiparticle separation happens, and then it starts to conduct current. So it's like 10 to the 12, and this only occurs at extremely high, ridiculously high electric field. So you don't need to worry too much about this in real life. Okay, here's one final page that I want to cover this thing, just to give you some refresh about the dielectric breakdown phenomena. So you know that Pikachu have a very famous signature skill of 100,000 thunderbolts, 100,000 volt thunderbolts. Okay, so thunderbolt is a lightning. So you need to use a dielectric breakdown phenomenon in order to this happen. And then from the previous slide, we know that the dielectric strength of air is 3.0 megavolt per meter. Okay, so 3.0 dielectric strength is 3.0 megavolt per meter. And then it seems like Pikachu can only generate 10 to the 5 volts, right? And then assuming that side up here is grounded, what I mean grounded is V is 0, okay? And then Pikachu can be as high as V equals 10 to the 5 volt. Then how close they should be in order to create lightning? Can you tell me the answer, like in the chat box? How close they must be in order to create lightning, or in order to induce dielectric breakdown? So mega is 10 to the 6, right? So dielectric strength is 3 times 10 to the 6 volt per meter. Pikachu can do only 10 to the 5 volt. Then how close they need to be in order to have this amount of electric field? Right. One over 30 meters, 3 centimeters, right? So I would say this is just, I cannot say this is even range attack, right? 3.33 centimeter is just, you'd better just a punch on your opponent. So that's why you need an upgrade, right? If you need become an, if your Pikachu become a Raichu, this becomes, I forgot, like 10 to the 8 volts based on their name. It's 10 to the 8 or 10 to 7, or 10 to the 8, I guess, 10 to the 7. Anyway, 100,000 volt or 1000 volt. I forgot which name it was. But if you do an upgrade, then your range becomes now become reasonable, like a few meters or a few tens of meters. Okay, and it becomes a real range attack. All right, so this is just a refreshment, and from next time we're gonna learn about like Gauss law in material, and then try to do some exercises in order to understand why this distinction between E field and D field and P field are required. So yes, this is it for today.